Let's talk about graphing sine and cosine. So let's start with sine. And typically we're going to graph it as y equal to sine of x. Now, I don't want you to confuse this with the unit circle. This is not where we're like saying x is cosine and y is sine. I know that's something we say like with the coordinates, that sine of an angle and cosine of an angle are the y and x coordinates respectively. I said that kind of backwards. Here we're just using y and x because we're going to graph on the xy coordinate system. And typically when we're graphing sine or cosine, we usually think about graphing one period of sine or cosine because sine and cosine are both periodic functions, meaning after one full period, one full rotation through the unit circle, they repeat themselves. So we know that, so we're going to go one full period's worth from 0 to 2 pi. And we could plot a bunch of values. I really don't want to. You really don't want to either. I will, like, if you look at the previous notes, you will see that I found a bunch of values of sine. Right, I went through kind of the whole entire list of every special angle. And sine of 0 is 0, and sine of pi over 6 is 1/2, and sine of pi over 4 is root 2 over 2, and sine of pi over 3 is root 3 over 2, and sine of pi over 2 is 1. So you go from these values that get from 0 that get larger and larger and larger up to 1. And then you kind of go through the same values back down to 0, right? In the second quadrant. So in fact, I'm gonna go ahead and say this. Right, here's quadrant 1. Here's quadrant 2. Here's quadrant 3. And here's quadrant 4. And through quadrant 1, we go up from 0 to 1. In quadrant 2, we go back from 1 down to 0. In quadrant 3, we go from 0 down to -1. And in quadrant 4, we go back from -1 up to 0. But we always hit the same 3 values, 1/2, root 2 over 2, and root 3 over 2. Sometimes they're negative and sometimes they're positive. I don't think of any of that when I actually graph sine or cosine, but that knowledge should be there. You've seen these things, we've talked about them, but here's what I want you to really think about when you're graphing sine or cosine. There's my unit circle. Here are the 4 corners of the unit circle that break the unit circle up into 4 quadrants. This is the point 1, 0. This is the point 0, 1. This is the point -1, 0. This is the point 0, -1. Right? I've gone 1 to the right, 1 up, 1 to the left, 1 down. And the angles are 0 radians, pi over 2 radians, or 90 degrees, pi radians, or 180 degrees, 3 pi over 2 radians, or 270 degrees, and 1 full revolution is 2 pi radians, or 360 degrees. So what I really want to do is just plot the values at these 1, 2, 3, 4, 5 angles, which breaks this up into 4 equal quarters, or 4 quadrants. So whenever I'm graphing sine or cosine, I'm going to take my full period length, and I'm going to immediately break that length up into quarters. So I'm going to cut it in half, and then each of those halves in half. So I'm going to cut that in half, and then each of those halves in half. There are other techniques for graphing sine and cosine, but I feel like this is the most, again, I'm all about efficiency when I'm doing my math. I really want to not spend more time than I need to and still get enough information down. So I find this method to be efficient while still kind of getting all the important information. So this angle is pi over 2, pi, 3 pi over 2. And more generally, what I'm going to say is, whenever you're graphing sine or cosine, the 5 points, I call them the 5 important x values that are on there, are always going to be exactly where you change from one quadrant to the next quadrant. And if it's just sine of x, it's always going to be these 5 values. It's going to, these might change depending on if we stretch or shift something. Oh, the lights went off. Okay, so got to figure out how to do something about that. It's there every class. Oh, anyway, so Now I'm just going to plot the points. Sine of 0 is 0. Sine of pi over 2 is the y value, which is 1. Sine of pi is the y value, which is which is 0. Sine of 3 pi over 2 is the y value, which is -1. And sine of 2 pi is, well, sine of 2 pi should be the same as sine of 0 because they're literally at the same coordinate, which has the same y value. And then you could repeat the process, right? If you kept going, I just want to point out the periodicness of this, right? If you kept going around, the next pi over 2's worth would be 5 pi over 2, and sine would be 1 again. And at the next thing here, which would be 3 pi, sine would be 0 again. And at the next angle down here, which would be 7 pi over 2, sine would be -1 again. And 2 full revolutions would get me to 4 pi, and it would be 0 again. So it really does repeat itself every period. And then we try to make it look nice. So before I draw it, let me show you what it looks like in Desmos. Because it's good to try and make things look accurate. So I'm just going to graph y equals sine of x. And there it is. And look, when you graph it in Desmos, it even kind of points out the important points that I was mentioning. That's kind of great. Desmos knows what we're going for and is thinking about what we're thinking about. I mean, it's not thinking, it's programmed to show you the things that you're most likely to be thinking about. So those are all the points we really care about graph. I mean, I don't care about this lesson so much. If I'm only doing one period, I want these 1, 2, 3, 4, 5 points. These 1, 2, 3, 4 equal quarters of the graph. So it can be hard to make this look right the first time. You don't want it to be too pointy. And then it just does the same thing. One way to kind of think about it, and this is kind of, I don't know. Oh, sorry, I was drawing it and you guys were seeing the wrong screen. Sorry. You didn't see my excellent drawing skills. And now you can see what I've drawn. It turned out okay. One thing I've noticed over the years that you might also notice is essentially it's just this shape, right? This first quarter of the graph repeated 4 times in a different orientation. In this next one, it's flipped over that way. And then the next one, you take that and you flip it over that way. And then the next one, you take it and flip it over that way. But it's always literally the same kind of shape, just in a different orientation. A couple important things to notice. I know this is a little bit, not beyond, but just, we don't have to talk about this. I would say that the domain of y equal to sine of x is all real numbers. I know we've only talked about taking the sine of like special angles and some other angles, but technically you can take the sine of any value and get an answer. And more importantly, the range is -1 to 1. It is always, always, always true that no matter what angle you're taking sine of that angle is always between -1 and 1, 100% of the time. But back to the original point, if you're graphing a trig function like sine or cosine, which are as a category are called the sinusoidal functions. Sine and cosine are both sinusoidal functions. If you're graphing one of those, it's going to look like this. And what I really want you to graph when you're graphing this is these 5 points connected in this nice way. And then typically when I'm graphing it, the graph doesn't just stop at the end. So we usually draw little arrows continuing on in each direction, so that the person reading is like, oh, they didn't just graph that part. They know it keeps going. Oh, and there's a chat. Sorry, I keep the chat open. Right, exactly, Karen. Range is, oh, sorry. You're correct. When you send me a direct message, I usually try not to say your name. I apologize, but you're right on. The range is exactly how high and how low the graph can go. So this graph goes as high as +1 and as low as -1. And it is definitely a useful and important piece of information that sine, and we'll see also cosine, are always between -1 and 1 to start with anyway. We use that fact a lot in future classes for a variety of reasons. Okay. So there's sine. And the way I remember how sine looks, because it looks a lot like cosine, is that sine starts in the middle and then goes up and then goes back to the middle and then goes down and then goes back to the middle. That's kind of it. And each of those 5 important points are equally spaced out. Okay, now let's graph cosine. In fact, let's kind of be smart about this. Let's keep the unit circle right there, so graphing cosine is even easier. So I'm using these 5 or 4 points on the unit circle very often when I'm graphing sine or cosine, at least at the beginning. So if I want to graph y equal to cosine of x, I'm going to do the same thing. I'm going to mark off approximately 2 pi. Now I wouldn't actually do mark 1, 2, 3, 4, 5, 6, and then say 2 pi is a little bigger. I would just say there's 2 pi, and I'm going to cut it in half and half again. And then 2 pi is about 6. I'm going to try and make this about 1. But your graph doesn't have to be perfect, right? Is that really 6 times as long as that? Maybe. It's close enough. So then cosine of 0 is going to be +1. And cosine of pi over 2 is going to be 0. I should label these. And then cosine of pi is going to be -1. Cosine of 3 pi over 2 is going to be 0. And cosine of 2 pi is going to be back to 1. And so this looks like the following. Sometimes I also like to look at where negative pi over 2 is. It's kind of like that. I will say, when you're reaching a point that's either at the top or the bottom, you want to kind of plan for that, right? When I'm coming towards this point here, I don't want to actually go further lower than that. I want this to be the very bottom of my trough and then to keep going up. And then I want this to be the very top of my hill and then to start going down after it. So you got to plan for when you're graphing these things, like, oh yeah, I know that's the top, I know that's the bottom. Something else I will say is that looking back at the unit circle, the x coordinate, which is cosine, always alternates between a 1 and a 0. 1, 0, -1, 0, 1, 0, -1, 0. So it's always going to be a 1, which is a top, and then a middle, which is a 0, and then a -1, which is a bottom, and then a 0, which is the middle. So I always think about sine or cosine kind of doing this top, middle, bottom, middle, top, middle, bottom, middle, top. It just goes on. Same is true for sine. It starts in the middle, middle, top, middle, bottom, middle, top, middle, bottom, right? But it's always a top, then a middle, then a bottom, then a middle, then a top, then a middle. How do we get the points again? Which points do you mean? Like the y coordinate or the x coordinate part? Both. Okay. So, I mean, technically you could graph a ton of points, right? Like I could also plot, say, like, for example, for sine of x, I could go back and throw in, say, x equal to pi. Oops, that's not a great pen. Pi over 6. And sine of pi over 6 is 1/2. Wow, this pen is terrible. I should just throw it away. Yeah. But the way we're getting these particular values is we're using the unit circle, because we know that on the unit circle, if the angle is theta, then the coordinates on the unit circle, like this coordinate here, 1, 0, or this coordinate here, 0, 1, the coordinates give cosine of the angle and sine of the angle. So this point right here has an x coordinate of pi over 2. and a y coordinate that is sine of pi over 2. But that's 1. So that's how we're getting the points, is by using the unit circle and using the input as the angle, that's our x, and the output is sine of that angle in this case, or in the second graph, cosine of that angle. And just like sine, we see that cosine also has a range of -1 to 1. And the domain is everything, all real numbers. So again, I'm going to say when you're graphing sine or cosine, you typically want to focus on plotting these 5 points. These 5 points that correspond to the 5 or the 4 + 1 quadrantal angles, right? I'm really just using this quadrantal angle, this quadrantal angle, this quadrantal angle, this quadrantal angle. That's it. And do interject if you have questions. I think it's good. I should also mention, right, this graph does go on. I'm only drawing, so when I'm drawing this, I'm really answering the question that is draw or graph one period of y equal to cosine x. So we graphed one period and a little bit more just to show that it kept going. So let's talk about the next part of this, which is shifting these graphs around and stretching these graphs in a vertical way. I feel like I've got so much room here. I should almost use it. No, fine. We'll just use a new piece of paper. So we'll talk about amplitude and vertical shift, also called a vertical transformation. Didn't quite mean to draw my line through my words like that, but still readable. So this is for some a, or I should say y equal to some a times sine of x plus d, or y equal to a times cosine of x plus d. So we're going to talk about the effects that both a and d have on the graph of sine or cosine. And here's what it is. The amplitude is how far from the middle the highs and lows are. So in the previous one, in the previous two, the amplitude is 1 because the high is 1 away from the middle and the low is 1 away from the middle. There's an easier way. This does definitely have relation to sound or frequency waves. Sound and frequency waves are very much sinusoidal functions. So while it's nice to have that kind of visual interpretation that it's just how far above and how far below the middle, the easier way to calculate the amplitude is just by taking the absolute value of that coefficient. So even if you're graphing, say like y equals, in fact, let's just write a couple examples. Y equals 3 sine of x, the amplitude is equal to 3. Or y equal to -2 cosine of x, the amplitude is equal to +2 because it's the absolute value of -2. And then actually let's graph one and then we'll talk about the vertical shift. So let's graph y equal to 3 sine of x. And all that's going to happen is that the y values are going to be 3 times as large as they were before. So if you want to make a little table here, with the x values, which are the angles, and the y values. And let's grab a red pen here. Let's do sine of x in red, and then 3 times sine of x in blue.
Your video box is like covering that.
Thanks. Yeah, I know. I wish it wouldn't do that.
No,
It's so annoying. But yes, thank you. I appreciate it. Okay, there. Now we can see it. Cool. So we're going to pick the usual angles, the usual quadrantal angles. 0 radians, pi over 2 radians, pi radians, 3 pi over 2 radians, and finally 2 pi. And we already know what sine of all these are. Sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is -1, sine of 2 pi is 0. Again, I'm just getting those from the unit circle again, right? The y coordinates of the unit circle. And then 3 times sine of x is literally just 3 times all of these numbers. 3 times 0 is 0. 3 times 1 is 3. 3 times 0 is 0. 3 times -1 is -3. 3 times 0 is. So it's going to look a lot the same, except it's going to be stretched out vertically. So here's 2 pi, cut it in half again. And then let's say that's 1, -1. So I'm going to graph just regular sine of x in red first. So I know I start at 0 and then 1 and then 0 and then -1 and then 0. So it's going to look like this. I'm going to draw it dashed because it's not the graph I'm actually really drawing. And then 3 times that, well, I can plot it. When x is 0, 3 times sine of x is going to be 3. Sorry, when x is 0, 3 times sine of 0 is going to be 0. When x is pi over 2, 3 times sine of pi over 2 is going to be 3. Right, it got stretched up to be 3 larger. And then for pi, we get 0. For 3 pi over 2, we get -3. And for 2 pi, we're back at 0. So this stretched out graph is going to look like this. Still got the same shape, but it's been stretched. It's been pulled up this way, away from the y-axis. And again, if you wanted to, you could totally look at this on Desmos. I should just maybe be sharing my whole screen. I don't know. It's kind of.
how did you get the I guess the numbers for like the 3 sine x on that graph that
Right. So this is just, so I just took these numbers and multiplied them by 3.
Oh, okay. Got it.
Good question, though. So we can also, right, you could totally say, what does that look like? I know we just graphed it. But look, you can totally see that. In fact, something even neater you can do, here's something you can do with Desmos, is instead of using 3, you can just plug in like a letter for a constant. And then you can add a slider, and then you can see what happens if k gets bigger and bigger and bigger. Oh, look at that. It's kind of cool. And then also if k is negative, or actually, this is kind of cool. If k is less than 1, but still positive, right? It's a smaller graph. And then if k goes negative, it flips over. Kind of neat. Helps to see what's happening. Whoops, I didn't mean to stop sharing. I meant to share my other screen. Okay. So that's what changing the amplitude does. Is it either stretches it up or it squashes it down if your amplitude is smaller than 1. Come on. So while I could graph, so the thing is, like, it feels kind of silly for me to graph these things because I could show you them on Desmos. So but I do think I should show you because I'm just going to expect you to be able to do it without just using Desmos. So let's do another example of an amplitude change. So let's graph y equal to 1/2 cosine of x. And this is going to, quote unquote, squash the graph. Whereas this previous one, this definitely stretched the graph. And just like before, we're just going to take our previous cosine values. In fact, we can make a table again, or in fact, let me actually not make a table. Let me just graph cosine for you. I'm going to graph cosine in red. So again, I'm going to go pi. So all the way out to 2 pi is my period. Usually the height would be 1 and -1. Cut it in half, cut each of those in half. And then cosine starts at the top and then goes to the middle and then goes to the bottom and back to the middle and then back to the top. And cosine does this kind of deal. Now, 1/2 cosine, all the y values are going to be half of what they were. So at this first x coordinate of 0 radians, instead of having a y value of 1, we're going to have a y value of 1/2, because 1/2 is half of 1. And at the next one, half of 0 is 0. And at the next one, half of -1 is -1/2. And the next one, half of 0 is 0. And the next one, half of 1 is 1/2. So it definitely looks like I took my original graph and I just kind of squashed it down like that. Again, Desmos is a nicer tool than my hand-drawn graphs, right? You can definitely see with this graphing tool, I can click these off for a second. I can do y equal to cosine of x. Great, beautiful, lovely. And then we can do y equal to 0.5 cosine of x. And look, oh yeah, it just smushed it down. I got it like that. Sorry, I'm doing things that you can't see me do them because I'm not on video right now. Sorry. Brain work. Okay, great. So when you have a vertical stretch, or I should say, when you have a different amplitude, that's going to give you a vertical stretch if the amplitude is larger than 1, and a vertical squash if the amplitude is between 0 and 1. And we haven't talked about negative amplitude, or not negative. We haven't talked about negative coefficients yet. Yeah, so what I will say, actually, I'll say that right now. So if the absolute value of A, which is the coefficient, right? That's our A. In the previous problem, this is what we're calling A. If the absolute value of A is larger than 1, we stretch vertically. And if the amplitude is less than 1, we squash. Or some people use the more technical term compress, but saying squash is way more fun than saying compress. Yeah, and then I'll just point out, although we're kind of not there yet, but it seems like worth knowing. If A happens to be negative, which we'll address later, but I'm going to say it now anyway. If A is negative, we flip the graph across the x-axis. Or more technically, we reflect the graph across the x-axis. And just to show you a quick example of that, no, my sharing skills are off today. Sorry, I'm losing it sharing wise. Brain work. Okay, so for example, if instead I had, -2 cosine of x, I took my cosine graph, stretched it by a factor of 2. So like this red one, right? You took the purple one, which is the original, stretched it by a factor of 2 to get the red one. and then flip the red one over the x-axis to get the final result, which is y equal to -2 cosine x. So there's the original, there's the stretched flipped version of it. Okay. The other thing that we want to talk about when graphing, well, not the only other thing, the next thing that we want to talk about when graphing sine or cosine is a vertical shift. So you can move the graph up or down simply by adding or subtracting something on the end. So let's just do some examples. I want to graph something on paper that doesn't have dots on it like that. Let's graph, say, y equal to sine of x plus 2. And all that's going to happen here is we're going to take all of our y values and they're all going to increase by 2. So if you wanted, we could totally make a table. Let's make a table. So again, I'm using the typical x values that are my quadrantal angles: 0, pi over 2, pi, 3 pi over 2, and 2 pi. And then we know sine. The sine of 0 is 0. Sine of pi over 2 is 1, then 0, then -1, then 0. And then all I'm going to do to get this graph is take these values and add 2. 0 plus 2 is 2. 1 plus 2, 3. 0 plus 2, 2. -1 plus 2, 1. So there's my new y coordinates. So there's my 2 pi again, half, half, half. So those are my 5 important x values, or my 5 important angles. And then I'm going to shift this up to, so here's what I usually do when I draw this. First of all, when I'm trying to get my scale, if I'm trying to get it to be close to right, I always think about pi being close to 3. So pi over 2 is close to 1.5. So if I kind of took this here and put it over there, that would be about 1.5. So then I'd like shift it down a little bit and be like, okay, that's about 1. It's not an exact process, but it does help you get it kind of close to being similar scale. Good question. So someone asked, are we always going to use these x values, or are there going to be instances where we have to go beyond 2 pi? I would say the answer is actually no to both. So no, we're not going to always use these x values, and they're going to change when we start changing the length of the period or doing a horizontal shift. So we've been dealing with vertical stretches and vertical shifts, which don't change the period. But when we do a horizontal stretch or a horizontal shift, that will change the period, which will change these quadrantal angles. So yes, we will be using different x values, but I guess sometimes we might go beyond 2 pi, but we'll never go beyond the whole period. But sometimes the whole period will go beyond the length of 2 pi, is what I'm trying to say. So here, I know my lowest value is 1, my biggest value is 3. But here's the trick I really think about. When I'm shifting something up or down, I think about how the x-axis is shifting. So the x-axis is just another name for y equals 0. Right? If you're living on the x-axis, you're living on y equals 0. Because no matter where you are on this, the y coordinate is 0. And so what I'm going to do is I'm going to think about how the x-axis shifts. Well, I'm adding 2 to everything. So I'm going to shift this up to y equals 2. And what I like to think about is I'm shifting the middle line. So if you haven't done a vertical shift, your general middle line is just the x-axis. Right? In our previous graphs, all of them were equally above and below the x-axis. So I call the x-axis the middle line. If I could use my thumbs, right? All of them, the middle is the x-axis. But now that's changing because we're moving it up 2. So my new middle is up 2, which is 2. And then we're going to say, okay, I'm going to start at 2, and then I'm going to go up to 3, and then back to 2, and then down to 1, and then back to 2. So here's my new sine graph. Ooh. It's just my old sine graph all moved up 2. I will mention that the range here is, instead of -1 to 1, now the range is going to be +1 to 3. Or you could say sine of x plus 2 is between 3. In a similar way, we could also graph cosine of something shifted. Sorry, that's not very well said. We could graph something like y equal to cosine of x minus 1. And again, all that's going to do is going to move the entire cosine graph down 1. So still the usual period of 2 pi, still breaking it up into 4 equal sections. You're always breaking your period up into 4 equal sections when you're graphing sine or cosine, at least if you're doing it the way I suggest you do. And then we're going to shift everything down 1. So I don't really want to draw all the points or plot or make a table with all the points. I just kind of want to say what it is. So I know usually cosine looks like this. Starts at the top, goes to the middle, then to the bottom, then to the middle, then back to the top. But now all those values are going to be 1 lower. So instead of being 1, 0, -1, 0, 1, I'm going to be 0, -1, -2, -1, 0. Or I'm going to think about drawing a new middle line. So there's my new middle line at y equals -1. You don't have to label it. I just like to label things on my graph. So I know that cosine usually starts at the top of its range. And that's like actually, I want to say a little more about that. Whenever I'm graphing cosine or sine, I always kind of remember that cosine starts at the top and does this top, middle, bottom, middle, top thing. Whereas sine starts at the middle and goes middle, top, middle, bottom, middle. That's kind of always the way they work, unless you've changed them in some strange way that modifies how they work. But if you've got just kind of the basic graph, it's been shifted up or down or stretched vertically, it's always going to have that pattern. So cosine is going to start at the top, which is 0, then the middle, then the bottom, at each of the corresponding next important x values, then back to the middle, and back to the top. Oops, I missed my point there. Be a good time for some whiteout. And again, I think this is really easier to see via Desmos. So let me share. Let me turn this off, oops, off. So here's my cosine graph, and we can definitely add, oops, yeah. We can add or subtract, right? There's cosine of x plus 1. There's regular cosine of, there's a way to do this where the numbers are like nicer. Yeah. Awesome. That's nice. So there's cosine of x plus 0. There's cosine of x shifted up 1, shifted up 2, shifted up 3, right? It's literally just moving the whole graph up by 1 or down, right? There's cosine of x minus 1, cosine of x minus 2, et cetera, et cetera, et cetera. And you can see, ooh, can I be smart here? Maybe I can be smart. Yeah, look at that. That's cool. So you can also see the middle line. It's kind of fun. Like, honestly, I could play with this graphing thing all day and be like, yeah, cool, look at that. It's pretty neat. But the point is that when you're adding something on, so that's a good question. Can Desmos be used during exams? The answer is probably not. Most teachers are probably not going to want you to be using Desmos during exams. That said, it's a really useful tool for understanding things, right? I don't think it's the intent, at least my intent, is not for you to use it during a test. It's for you to kind of make sure you understand things as you're doing them, like with homework. But there are definitely times when teachers assign problems or things with graphs, and the expectation is that there's no way you can actually graph that on your own. The expectation is, oh yeah, you used a graphing utility to be able to see what that thing looked like. Let's see, what else am I trying to say here before I run out of time? No, I think that's kind of it. So the only thing left, well, not the only thing left, the only thing left today is to talk about kind of putting these two pieces together. So eventually, I think next class, we'll talk about kind of putting it all together with the horizontal shifting as well. But for now, let's talk about some graphs that have a vertical shift and a vertical stretch. So let's look at something like y equal to 3 sine of x plus 2. And so really, I want to think about all the things I'm doing, but I don't want to draw all the things I'm doing. Not because I wouldn't, but because I don't want you to do that, right? I don't want you to draw like 3 different graphs to get to the final result. I want you to be able to start with thinking about what sine looks like. And again, here's a quick and dirty sine. Oh, wow, that's very not good, right? That's kind of the worst sine I've probably ever drawn. But there's let me try that again. Let's try that, making that a little bit better. There's a very kind of, okay, that's 1, that's -1, that's 2 pi. There's sine of x, right? Not that we need that, just to kind of have an idea. Here's what we're going to do. The 3 is going to stretch it vertically. So instead of going from -1 to 1, it's going to go from -3 up to 3. And then the +2 is going to shift everything up by 2. So that's what I'm going to try and graph at the very outset. I will also say, specifically when the period is nice, like 2 pi, you can probably get away without labeling the rest of these points, because we all know what they're, well, everyone's going to assume you know what they are if you just do that. It's probably good to label them though, until you're absolutely sure of everything that's going on. Okay, so I'm going to take my graph and I'm going to shift it up 2. So my new middle line is going to be 2. And then my amplitude is 3, meaning I'm going to go 3 above the middle and 3 below the middle. So 2 plus 3 is 5, and 2 minus 3 is -1. And then sine has this shape: middle, top, middle, bottom, middle. That's honestly what I really think of when I'm graphing sine: middle, top, middle, bottom, middle. So the middle is here. At the next important value, the top is 5. Then at the next value, we're back to the middle. The next value, we're down to the bottom. Next value, we're back at the middle. For any sinusoidal graph, sine or cosine, you should always end at the same y value that you started at if you're doing one full period. So it's going to look like this. You have to make the sound effects move up. All right, good. Excellent. There's my 3 sine of x plus 2. And I don't need you to label these points, but in case you're curious, right, this point is the point 0, 2. This is the point pi over 2, 5. This is the point pi, 2. This is the point 3 pi over 2, -1. And this is the point 2 pi, 2. And these, at least when I ask you to graph sine or cosine, these are the 5 points I expect to see. the points where we're using the quadrantal angles to find the highs and lows and all the middles. I don't care about this point. I don't care about that point. This point's garbage. I mean, they're all important points, but the points I really care about are these. That making fun dancing motions, but the lights go off. That's also what I really care about. So I should also mention, most of the times in your future, when you graph a thing, I would say 80 to 90% of the time when you graph a thing, someone's going to ask you to find the x-intercepts as well as the y-intercepts. This is definitely an exception to that. There is absolutely zero need for me to have you find this x-intercept and this x-intercept. The only exception to that for sine and cosine is specifically if the intercept happens to be like here, right? In this graph where we did cosine of x minus 1, we would want to know the x-intercepts because they happen to be exactly your top points there. We're out of time. Yeah, so here's what I'll say. On the old notes, there are 2 more examples, which I would encourage you to look at. You can't, of course, my document camera here. So there are 2 more examples of graphs that are worth checking out. And what I would strongly encourage everyone to do when you're graphing these is try to graph them on your own. Like really, graph them without help at first. But then look at Desmos for every one of them, just to see like, am I doing it right? Right? You can definitely, and I kind of, let me play with things here for a second. Often, I would also kind of encourage you to do it step by step. So like if I was actually graphing y equal to, sorry, I'm looking at Desmos and you guys are not. If I was graphing y equals 3 sine of x plus 2, I might, if I was desmosing it out, if I was trying to see what was happening on Desmos, I would maybe go step by step. So I might do just the plus 2 part first. I would actually like to see this graph maybe. So there's y equals sine of x, and where there's y equals sine of x plus 2. Oops, not plus of 12. And then I can do, oh, come on, y equals 3 sine of x plus 2. So you can kind of see how that works. Or if you prefer, you could also kind of look at the stretching first. Now it gets kind of messy if you have all that on there. So it might be nice to be like, okay, well, there's y equals sine of x. And then if I stretch it out, there's y equals 3 sine of x. And then if I shift it up, there's y equals 3 sine of x plus 2. So I really think there's a lot of tools at your disposal. And I greatly encourage you to share to look at them. Sorry, just trying to go back to this screen here. So yes, I would really, oh, I know it. Sorry, I just remember, I forgot to pin my video. Not that's a huge deal, but it means I might have to do more work in the editing later. Anyway, not your problem, that's my problem. So last thing I'll say, and I know I'm out of time, is that when I'm graphing sine, I'm thinking what the middle line is, what the top and the bottom is, and then I know sine goes middle, top, middle, bottom, middle. So if you can identify what those highest, lowest, and middle values are, it's going to be pretty easy. And I will also say the middle is just how much you shifted it up or down, and the top and bottom are just the middle plus or minus the amplitude. Now you have a question?
Yeah, I was wondering if I remember doing this last year, and I did a little different the graphing, and I just want to make sure with you if that's okay. So what we did is when it said like +2 or minus or anything, instead of doing the 0 on the axis, we started like if it said +2, it would start at 2. And then if I add an amplitude of 3, it would be +2 would be the 5, and then
Yeah. No, that's I feel like we're saying the same thing almost, just maybe slightly differently.
yeah,
Like
just that, yeah, less drawing.
right. Yeah. So definitely like if I was doing this one, I would essentially I would think of this as my new x-axis. And then I'm going 3 above and 3 below to get the tops and the bottoms.
Yeah, but is it okay if I don't like, if I just start my graph at like 2?
I see what you're saying. I would like you to draw the XY coordinate system.
Okay.
Yeah, that's a good question. I do think so. Yeah, I think that's what she's saying. So like 2 is the origin. That is what you're saying. I would encourage you, I think, to not that you can't think of it that way, but I really do want, you should be drawing an X and a Y axis. But you can mentally pretend like, oh, well, I'm going to draw, you can draw this. It's totally fine to draw this. And then be like, that's really my x-axis for the purpose of my problem. And just to, sorry, there's one last thing I want to say. I know for cosine, the pattern that I always think of is it's going to be top, middle, bottom, middle, top. Lastly, I will say there's a lot of ways to do this. This is one way of doing it. This is the way I kind of think about it. But if you have something that already works for you, you should do it that way. My only request, well, I guess I have 2 requests. My only requests are that you do draw an XY coordinate system, and 2, that you get these 5 points. I don't care about any other points, but I do want to see the highs and lows and the middles. Nothing else matters. Or another thing is I want to see all the points that occur every quarter. So here's the beginning of the first quadrant. Here's the beginning of the second quadrant. Here's the beginning of the third quadrant. Here's the beginning of the fourth quadrant. Here's the end of one full period. That's what I'm really looking for. All right, I've talked more than I should have. I will stop talking. You all are free to go.